तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
Hello and welcome back to the lecture on CRT display devices. In the last lecture, we covered two of the three different type of CRT display devices. First was the DVST or direct view storage tube, and the second one was calligraphic or random scan display systems. Well, the difference between the two types of display systems which we discussed in the last lecture was that the DVST had a long persistence phosphor coating on the screen, and the random scan display system had a short persistence phosphor which used to decay in about 10 to 100 microseconds. So, it needed a refresh. So, we talked about a refresh rate of certain 30 frames per second to be done for random scan display systems, whereas in the DVST it was a long persistence phosphor, so it could stay for several seconds. The other difference between the two was that in DVST we also called it a vectored or a line or a stroke based system, in which we were essentially drawing lines on the screen. Okay? Even characters were made up of short segments or lines, and you want to draw any picture, we also had to draw lines on the screen. Okay? So, that was the essentially the random scan display system, and of course, in the DVST also we were drawing lines. The beam had to be switched on and off in both the cases. Now, we come back to today's lecture, which is the third category of the display system, called the refresh and raster scan display system. Okay? You can call it a refresh raster or a refresh scan or a raster scan. It is different from the calligraphic and or the random scan display system, and we will find out in what way it differs. Okay? Let us look at the screen. The first point is that the refresh and the raster scan display system typically is the most common standard used in modern display systems as well as in modern television screens. Okay? And how does it differ from the random scan display system? Unlike the DVST and random scan display systems, which were essentially line drawing devices, I just mentioned to you today, and we discussed at length in the last lecture also that they were drawing lines. Refresh CRT or a raster CRT is essentially a point plotting device. So, we are essentially putting points on the screen now rather than drawing lines, and how this is implemented or how this is basically performed on the screen, we will go through this lecture. The next point is the raster displays stored the display primitives in a refresh buffer. We talked about a refresh buffer in the random scan system, which had a display list or a display program and which had to be cycled at a certain rate, but in that case it essentially contained lines. In this case we will say that it entirely stores display primitives like lines, characters, shaded and patterned areas. We talked of these display output primitives in the introduction part of the lecture, where these are the primitives used for any graphic standards or for graphic softwares, and basically these are stored in the refresh buffer, and still these are all implemented by point plotting device. So, it is essentially we plot points corresponding to these display primitives. Refresh buffer is also called the frame buffer. It stores the drawing primitives in terms of its points and pixel components. So, this is an interesting point which I was just mentioning, that the frame buffer or refresh buffer stores the drawing primitives in terms of points and pixels. So, in the random scan, basically we were storing line commands to draw pictures, characters, whatever it is, or even curved objects are made up of lines. In the case of refresh buffer or frame buffer, we essentially store the point coordinates and the pixel intensity values for each drawing primitives, and typical example of these drawing primitives, as you can see in the screen in the second paragraph or the second line, says that the primitives are lines, characters, or shaded and pattern areas. So, this is essentially the difference between the DVST and random scan on one side and the refresh or the raster scan on the other side. Okay. Now, to implement this point based method of drawing, there are various facets, concepts and principles in the refresh and raster scan display system, which is not present in the other two types of display systems, the DVST and the random scan. We will talk of concepts such as the amount of memory needed in the frame buffer, the pixel access time, the bandwidth. So, these are all concepts which will come in here, and they are much more important in this lecture, or when we talk about refresh raster scan, then when we talk about say DVST or the calligraphic or random scan display systems. So, before we talk about these concepts, let us look into the architecture of a simple raster graphic system. I think in the previous slide, in the previous lecture, we also talked about simple architecture for a random scan system. So, this is almost similar to that. I will say in this case, a typical computer system will have its own CPU, system memory, system bus, I/O devices, and a video controller which drives the computer monitor. We have seen the internals of a computer monitor in terms of its electronic gun, and of course, the horizontal reflection plates, the control gate, the focusing system, and the phosphor coated on the screen. We also talked about the frame buffer being part of the system memory, which we will come to that, but this is a simple system where we say that the CPU puts the frame buffer instructions somewhere in the system memory, and the video controller gets the output primitives, the point and the pixel commands from the system memory, and takes it out and displays into the monitor. So, the video controller has a particular task. We see the block diagrams inside the video controller of what it is doing in due course of time. Well, as I was talking about, slightly elaborated architecture of the raster system with a fixed portion of the system memory reserved for the frame buffer. As I was talking about, that you can say that the system memory and the frame buffer together can be conceived or visualized as a single memory module of the system, or you can have a part of the system memory, or the RAM as it called it, identified as the frame buffer, where the CPU or the application program puts the instructions in terms of the display list or display program, which we talked about in the case of random scan, that is put inside the frame buffer, and video controller will access the frame buffer through the system bus and display contents in the display monitor. Well, a few other points. Another important point, which is a distinguishing fact between the refresh and raster scan display systems on one side and the line based display system. I will call it as a line based. The random scan, calligraphic, or the DVST are essentially line plotting commands, stroked, vectored, or lined. In this case, it is a point base. So, when you are talking of points, we have to now visualize that the screen in the case of a refresh raster scan consists of a matrix of points, or what are called as integer pixels, or simply pixels on the screen. The screen which you are seeing in a modern television or modern monitor, display monitors, computer monitors, or even LCD panels essentially consists of an array. You talked of an array. In mathematical algebra, it is an array or a matrix of pixels, and the entire screen uniform, instead of having a uniform coating in the case of a DVST or even the random scan which used to draw lines. Now, since we have to draw points, so the points are at specific locations on the screen. So now I want to draw a point at a coordinate x comma y inside the screen. I must access only the corresponding pixel, which is a small dot on the screen, which illuminates when an electron gun fires an electron beam into the spot on the screen. The point starts glowing. So essentially there are a few million points on the screen, which we will call as a matrix of pixels. That is the difference between the line based and the point based. Each pixel brightness can be controlled. That's the same case in the that's the property of a monitor, which we used to do in the case of random scan or DVST. The brightness can be controlled by the strength of the electron beam, which is firing inside into the point, and the strength of the electron beam controls the brightness of individual pixel. Okay. The next point, refresh buffer can be visualized as a set of horizontal raster lines or a row of individual pixels. Refresh buffer can be visualized as a set of horizontal raster lines or a row of individual pixels. We talk, the concept is like a matrix. Matrix or an array where we have horizontal rows and vertical columns. So obviously we talk of these as horizontal raster lines. We don't bother right now for the vertical columns for the time being, but we assume that in an array or a matrix of pixels we have horizontal raster lines or row of individual pixels. Okay, that's what we'll, and that's very important. We'll see why we have to consider that rather than vertical columns. Okay, each point on the screen is an addressable point in screen or as well as in memory. This is interesting. That means when I was just saying that if you talk of any point, any arbitrary point with coordinates x comma y on the screen, and you want to access that by firing an electron beam onto the point on the screen, it is equivalent to trying to access similarly a memory location within an array or a matrix. Okay. In memory, you can also define a chunk of memory which stores the values of the matrix of pixels, and you access that particular addressable point in memory, and the contents are then transferred to the point on the screen. Basically what is done is the contents of that memory location will hold the intensity or color information of that point, which will in turn control the strength of the electron beam, which when fired onto that particular corresponding point on the screen will actually dictate how much of intensity you want at that particular point, what color you want at a particular point. So we will say there is a one-to-one correspondence between a point on the screen and the corresponding point in the memory array. Okay? Line cannot be drawn directly from one point to another. This is an interesting fact. We were not worried about points in the case of DVST or in the case of random scan. It was our basic unit. We use these lines and short strokes in vectored mode, drawing in the case of random scan or DVST to draw lines or characters or whatever complex pictures you want. But in this case, since we are only addressing and drawing points, now it means that a line, a short or a long one, has to be drawn with the help of points. That means you are basically not drawing a simple line by joining one point to another as you draw on the screen, but you basically have to enlighten or switch on pixels or points which lie between the starting point and the end point of a line. So basically you have to switch on points or draw points which lie between one point to another. A line cannot be directly drawn. Correct? It's not simply like putting a scale and drawing a line, or on a vectored mode, just switch the beam from one point to another after switching it on and a line is drawn on the screen. That is not possible. In this case, you have to switch on the points which lie between the end point and starting point and end point in the screen, and this is how you can draw the line. We'll see it as an example of how this is drawn, and later on in lectures when we talk of graphical output primitive drawing algorithms, scanline algorithms, we will see how this is implemented quite fast in a computer. But this has its own problem. We'll see again with an example which is unavoidable in the case of refresh and raster scan display systems, in the sense that this causes the effect of aliasing, Jaggis, or what we call as staircase effect. Okay, so we have the effect of aliasing, Jaggis, or staircase effect when we try to draw a line in the case of a refresh raster scan display system. This concept or this drawback doesn't exist in the case of DVST or random scan display systems. We will see with an example. Okay. The last point is a terminology which says that the refresh buffer or the frame buffer, its terms are again used interchangeably, is also called a bit plane. In this special case, actually it is called a bit plane, but you can generally call it as a bit plane or refresh buffer or frame buffer or refresh frame buffer. Okay. Okay. So we know that the raster scan display system draws a discrete set of points. It draws basically a discrete set of points, and this is done with the help of an example like this. This picture shows that there is a yellow cylinder on the top left which signifies an electron gun. Then there is a blue line coming out of the gun which indicates the electron beam, and the electronic beam is basically moving horizontally across the screen. Okay, this rectangle which you see with a border, assume it to be a television screen or the monitor in which you are visualizing this particular lecture or watching this lecture basically. And the electron beam, as it moves from left to right on the screen, remember it does not draw a line, because the raster scan display system essentially was drawing a line that would have been the case for a random scan, but in this case it has to put a point. So only at points where the beam is switched on you will find a point glowing on the screen, otherwise not. So what we are assuming now, when you see this horizontal line, black line on the screen, you assume that the beam is switched off. It will be switched on at only those points which you want to mark on the screen. Okay? So let us say the beam with the help of horizontal and vertical deflection plates or electromagnetic coil will be deflected from left to right on the screen. It will go down again and keep scanning what we call as horizontal row of pixels or horizontal scan line. So the first line is drawn but is not displaced because the beam is switched off. So the beam has moved from left to right, but you don't see anything on the screen. That line which you see is basically the trajectory over which the beam has moved, but since the beam is off, none of the pixels or points are on. So let's see what it does. After a few such scan lines, you will see an effect like this. What you will basically see is those points on the screen where the beam would have switched on. Okay? So if you take a particular horizontal line, let us say the top one here, if the beam would have switched on only at one point and switched off again, making that point or pixel to glow. At some point beneath, the beam would have switched on twice, one for the left pixel and one for the right pixel on the same horizontal scan line. So wherever you want these pixels to glow, to give the effect of a line, you have to make the beam turn on and then turn off very quickly, because the beam is traveling very fast from left to right on horizontal scan lines or horizontal rows of pixels, and it keeps doing this from line 1, line 2 and line 3 and so on. So at some intermediate stage you will probably find out that you let us say almost half of the scan lines have been covered, and at a few positions the beam have been turned on, and it is at only those points where the pixels are visible. More on that, the electron beam has now traversed more than 3/4 of the frame or the screen, and it has switched on and off twice for each scan line, giving the effect of two inclined lines. Okay, it appears like an inverted V for the time being, but since the picture is not drawn, I will not tell you what we are going to draw actually overall on the screen, but now it gives the effect of two lines meeting to form a corner or something like that. But except the first horizontal or second scan line where the beam would have switched on only once, at each other scan line at two integer pixel positions the beam would have turned on, and it is off for the rest of the period. So you basically, again I repeat, you don't see the horizontal scan lines. These are just the trace drawn on the screen to give you the visualization. What you essentially see are these pixels, very dense in general, but I have made it sparse to give you a visualization. So you basically see two continuous lines which meet at a top corner. Okay, that is what you see. At the end, after the entire picture is complete, it will look something like that. Probably I am trying to draw, in this case, let us say the effect of a triangle. Let us say that means I will probably draw one more line, and these two lines will probably converge at some other point in the bottom of the screen. So whenever you want the beam to switch on, to draw or make a pixel glow, or draw a point, as he was talking about in the case of a raster scan, the beam is switched on. Otherwise, for all other, you see for the simple picture which consists of 2 or 3 lines, the beam is essentially switched off for the majority part of the scan, for the entire frame. It is only switched on at 1 or 2 occasions, or 1 or 2 points within a line. So that is an important part of point based drawing for a raster scan display system. It basically, as the title says, it draws a discrete set of points on the entire screen, or even if you take a horizontal line, it may not draw a point, or it may just draw 1, 2 or a few more points for each horizontal row of pixel, or what is technically termed as a horizontal scan line. Well, we talked of problems in line drawing in terms of what is called as a staircase effect, or a Jaggies, or an aliasing problem. Several these terms are used interchangeably. They basically mean the same thing. We look into the screen and see 2 special cases of a line, a general line and a special case. This is what I mean by a general line. Correct? Let us talk about a horizontal array of pixels, or a matrix of pixels. And typically, there are 2 ways by which pixels are addressed, either in memory or the screen. We assume that there are the pixel addressable point are integer values, x comma y, horizontal and vertices, ordinate and abscissa, integer values starting from 0, 1 up to n, depending upon the resolution of the screen. Okay, and the addressable point is the intersection of any 2 such grids. Okay, and the picture element or pixel which grows basically on the screen can be visualized to lie either on the intersection point as shown by the addressable point on the screen, or it could be inside of that small square element of the grid. The picture element, as it is called, a pixel. In fact, the word pixel is coined by the combination of 2 words called picture element. Okay. Now, in this case, we want to draw a line from point A to point B. So point A is at the bottom of the screen as given here, and the point B is somewhere here. So unlike in the case of a random scan where the beam was moving from point A to point B, that's all right. What we do in this case is we have to switch on a set of pixels or points which lie close to the actual line joining point A and point B. There are many sophisticated algorithms. So we will talk about one such line drawing algorithm to find out which are these pixels which are the closest and gives the visibility of a continuous line for line AB. So which are the pixels to be switched on, but this is a particular example, as for example, the rasterized approximation to line AB means that you will not see this line, the dark line joining points A and B as talked about here, but you basically will see these gray shaded pixels, square blocks. They won't appear square because they are so small and finite that they will appear to be a continuous line, but if you observe very closely with the help of a lens, or sometimes even with the naked eye in case of a poor or a low resolution display system, TVs, screens, or even monitors, you will probably see that these pixels will form an arrangement like these, and these are the pixels which the algorithm has found out, or the program has found out, to lie very close to the line A and B. And this is the effect of what is called, you see an effect of a staircase here. It shows that it is an effect of a staircase. In general, you will have this. That is why we will call this picture A as a general line in which you have this effect of staircasing, okay, or Jaggies or aliasing problem for a line. This is true with the digitized world or discretized world, even in other areas of computer science and digital geometry or digitization or whatever you name it. This is bound to be there. You can't avoid it, in fact, and this is a case where how it shows what the general line means. Okay. Well, the special case of a line, this effect of staircasing, jaggies or aliasing will not occur in special cases of the line where the line is purely horizontal, purely vertical or inclined at exactly 45 degrees with respect to the horizontal line. Let us say these are three cases of lines. If you see, if I am taking 4 points, point A here on the figure B, I am talking about figure B, point A is on the left hand side bottom, point B is somewhere on the right bottom, D is on the top right and C is on the top left. So, if you see the pixels which are drawn for the line A to C and A to B being a perfect horizontal line, A to C being a perfect vertical line and the line A to B being a perfect diagonal line inclined at 45 degrees or pi by 4 radians. Okay? In these cases, we can almost assume that the pixels exactly lie on the line or just adjacent to it. In this case, does not matter, but it forms a perfect arrangement as desired for the line, and you do not have the effect of staircasing or aliasing as you see on the left hand side figure for a general line. But if you take all possible lines which can be drawn on a screen, you will see that the special cases do occur, but they occur rarely. So, general line occurs more frequently, and so you will have the effect of jaggies or aliasing or staircasing effect. I hope this concept is clear. We will discuss this later on when we come out of display devices and talk about algorithms for scan line or line drawing. This will be more evident. We will talk about that later on as we go. Okay. At the beginning of the lecture, I did say that there are certain concepts to do with refresh raster scan displays which may not be we may not be concerned about. Some concepts with DVST, when we are discussing about DVST or random scan display systems, there are some concepts which are not bothered, which we have to worry about in the case of raster refresh displays. There are two parts. One is to do with, of course, these points and line drawing, which we already talked about, but there are more to it in terms of the memory, amount of memory, the scan rate, the scan conversion, video basics. So, we will move into those concepts for refresh raster for the rest of the lecture today and even maybe in the rest part of the lecture. Okay. Well, we had already talked about that the raster is stored as a matrix of pixels representing the entire screen area. We already know that. Okay, I reiterate that point. And then we also seen with an example that the entire image is scanned out sequentially. We know that how it is done by the electron beam, and it is usually switched off, only switched on when you have to make a pixel glow. So, it is scanned out sequentially essentially by the video controller, which has control of the electron beam. So, it scans one raster line at a time, and each raster line it knows which pixels to switch on or off. Essentially, it is off, the beam is off, but wherever it wants to switch on, it will switch on and go off. Okay. The raster lines are scanned from top to bottom, we also know that, and then back again it has to go to the top. Why? This is obvious, because we have to refresh the screen. Okay. Unlike the DVST, both the random scan and the raster scan display systems have one thing in common: the persistence of the phosphor is too low. Okay, it will vanish in no time. It talks about 10 to maximum a few hundred, not even 100, maximum 100 microseconds. So, it has to be scanned. The pixel has to be visited again, otherwise it will switch on and off too early for you to have a consistent view. Flicker-free display is what we want, and to do that we know that we have to do a refresh, and so the refresh word is still there. Okay, but the raster has come in. So, we are essentially drawing points on each raster line, and they are scanned from top to bottom, and then we have to again go back to the top to start the scan once again. The intensity of the electron beam decides the brightness of the pixel. In the case of random scan, the intensity was dictating the brightness of a line. In this case, it controls the brightness of a pixel, and of course, the brightness of a line will be dictated by the brightness of all the pixels which lie within the line. Well, we at least have one memory bit inside the frame buffer, okay, which could be a part of the system memory, or it could be a part of the video controller. We will see that, but essentially when we talk of the adapter cards, typically they have a video RAM inbuilt in the card along with the video controller. which drives the monitor, but some part of the frame buffer could be in part of the system RAM, or it could be in the video controller. So at least one memory bit per each pixel, and in this case we talked about this point earlier, we call it as a bit plane when we have one memory bit for each pixel. Well, the architecture of a raster graphic system with a display processor. That's a slightly more elaborate diagram. We talked about this figure earlier on in several occasions in today's lecture as well as in the earlier one. The difference in this particular diagram or figure compared to those which were there in the previous diagram was the display processor. So that's the additional part, the rest of the CPU which accesses the display memory directly instead of the memory sitting through the system bus. That's the difference here. The configuration could differ, but the frame buffer is a part of display memory in this case, that, and the video controller takes the input from the frame buffer, drives the monitor, all that is fine. The extra part is the display processor. We need an extra display processor to do some jobs of computer graphics such that it helps us to avoid overloading the CPU or central processing unit. Well, the central processing unit has to do a lot of tasks in terms of managing the system, running the operating system, handling the input outputs and all that. We have a system memory down below, as you can see from the system bus, but we have a display processor memory and a separate display processor with its memory which the CPU can directly access, and the frame buffer is a part of the display processor memory, and the display processor basically does all the computer graphics, picture drawing, manipulation commands, and it frees the CPU from getting overloaded of the burden of doing these jobs connected to scan conversion, refresh rate and all that, because if the CPU gets involved in doing all these graphical image drawing manipulation commands which requires, we will see, a very fast bandwidth, very fast operation, then the CPU will be busy doing that, and the system will be devoid of resource of the CPU to run other programs, and the system will be very sluggish. The system will not be able to respond to other requests of other users for, say, non-graphical work, of applications which doesn't require much of graphics. The CPU will not be able to respond. So you have a separate, and it's almost a must in most modern day systems to have a separate display processor which runs the graphics application programs and the packages and access the display processor memory or the frame buffer to make the display list, the display program, which in turn will be driving the video controller. So that's the job of a display processor. Job of a video controller, it's very important. If you see from the, remember from the previous diagram, if necessary we will revisit it again, it basically gets the input from the frame buffer and drives the monitor. What do you need to drive to the monitor? You need to give input to the monitor two things: where the beam should be and what should be the intensity of the beam. I repeat again, the beam is being scanned from left to right, each scan line from top to bottom, back again to the top, that's fine. So at each point you must know where the beam should go, automatically the video controller will do that, and at any point of contact with the memory screen, the video controller must know whether the electron beam must be switched on or it should be remained off as it is, and if it is to be switched on, with how much intensity, what should be the strength of the electron beam such that the desired intensity level which is in the frame buffer for the corresponding pixel. Remember, there was a one-to-one correspondence between the two arrays or the matrix of pixels on the screen and also in the frame buffer. Each point addressable in memory, there is a corresponding point of the screen which should be off or on with a certain brightness or color. So when you are addressing that point in system memory or frame buffer, the corresponding, the beam is also trying to fire that pixel on the screen. So you must know what should be the intensity or the color of that point, and hence the strength of the intensity, strength of the beam must be controlled to give it the desired intensity at that particular point. So if you look back into the figure, essentially the video controller must give two outputs. First one, if you see within the pink shaded diagram here with white characters, horizontal and vertical deflection voltages, that dictates where the electron beam is currently and what pixel on the screen it is trying to access. Okay, So at that particular point, the deflection voltage of the horizontal and vertical deflection plates, or it could be the solenoid, the coil, magnetic coil, which controls where the beam position currently is, that is dictated by what memory you are accessing at the frame buffer. That is number one. And what should be the strength of the electron beam, whether it should be switched off, whether it should be switched on, the intensity of the beam. So these are the two outputs of the video controller which goes inside the monitor, or the monitor basically needs these two inputs from the video controller to guide the beam and switch on and off and the particular intensity. So these are the two outputs. I hope it is clear. Okay, what does it do? Well, you have a block called the raster scan generator, which will automatically keep doing this refreshing. We haven't talked about video basics and refreshing, we'll do that, but basically the raster scan generator keeps generating automatically these horizontal and vertical deflection voltages corresponding to the addressable point in memory from the frame buffer, and it will generate, it will load the corresponding values of xy coordinates of that integer position of the screen to two registers, x and y registers, which will in turn address memory through a memory address register. Well, this is something to do with concepts of computer organization and operating system. Those who have that background will easily understand this, that the memory address is built from the contents of the x and y register, and it will help you to access a particular location inside the frame buffer corresponding to the point you are addressing on the screen. Okay. So I repeat again, the point on the screen addressed and the point in the memory at the frame buffer must be addressed simultaneously. It is done with the help of this block diagram, where the raster scan generator generates the analog voltages for deflection of the beam. It also generates correspondingly the digital values of the x and y integer coordinates, which in turn will generate the memory address and hence access the point on the frame buffer. The frame buffer will return what? Once you address a particular point in memory, it will return the contents. So it will return the contents to a pixel register, which will hold the value of the intensity of that particular point which you want on that screen for a particular point. Two corresponding points are addressed simultaneously, one in the frame buffer, one on the screen. So you address them by the video controller. Deflection voltage is generated. Beam is already there. What should be intensity? The contents of the frame buffer are taken out and fed to a pixel register. Pixel register drives again a digital to analog converter to generate an intensity, basically a voltage which controls the strength of the electron beam, in which will in turn control the intensity or color of the pixel or point on the screen. So I hope this concept is more or less clear. In fact, it will be clear to those students who have some background at least of concepts of computer organization and even operating system little bit. Concepts of computer organization architecture are probably more important to understand this block diagram, where you access in the frame buffer a particular point, get the intensity through the pixel register, put that intensity voltage on the electron beam to dictate the strength of the beam or the intensity of the pixel screen, and the horizontal deflection voltages dictate where the beam is. Okay. So we'll get out of this. That's another way of visualizing the architecture of a raster display system. Now we don't worry much about the internals of video controller or the system. We typically look at the two bottom parts of the screen. I said that there is a one-to-one correspondence between the refresh buffer or frame buffer and the screen. Okay, so that's the left hand part. We talked about the refresh buffer being a horizontal array of memory locations. The screen is also a horizontal row of pixels. So the host computer typically will have a display commands and input output to a computer through the keyboard and the mouse. The display controller will now load the refresh buffer corresponding to what the display commands have, corresponding to the computer graphics application package which is trying to draw a picture on the screen. The refresh buffer will have a contents. Typically what I have done is try to put the refresh buffer assuming it is a single bit display system. So I have loaded 0 or 1. If you see on the bottom left the refresh buffer, it will have 0 with drawn with black and 1 is drawn with orangish color. So I am trying to draw a structure of something like a house with a moon on the top. The refresh buffer will have the contents as shown on the left. I repeat again, black zeros and the ones are in color. So, just to distinguish between two values, and that refresh buffer drives the video controller. The video controller will take the inputs of all the contents one by one and put it on the screen. The screen you will have probably a very nice picture as given on the right hand side, a house with a window and a door and the nice moon on the top on the sky. So, that is a typical example of a correspondence between contents of the screen and the refresh buffer. This diagram probably shows the 1:1 correspondence, if not explicitly, very implicitly within the picture. Okay. Well, this is a very good example. When we talk about raster scan with outline primitives, we are talking about points being drawn on the screen. So, a line essentially consists of points, okay, and these points help to draw a line, and this is again a very simplified picture of a house with a window, a simple example of just the outline primitives. We are drawing lines and curves with the help of points, and this is what will be also the contents of the frame buffer as what you will see on the screen. The background could be black and the outline primitives could be white or vice versa. It depends upon the way you want to represent this picture. Okay. So, essentially again this is a good example to show that you are drawing points, you never draw a line, and with the help of points itself you have to draw lines, curves or anything else within the picture. Raster scan will fill primitives, same diagram. Now, you want to fill area. Well, I have filled some parts with color to give it a continuous shade, but essentially filling is done by drawing lines with the help of again points. Remember, everywhere it is a point. Either you talk of the shaded area also will have points with a particular color or shade, and the inside of this house basically is filled with horizontal lines. You can fill it with vertical lines also, no problem. You can draw a line from anywhere on the screen to anywhere on the screen, but essentially you are only putting points. So, this is a fill primitive where the region is filled with a certain gray shade or color. Okay. You can have an outline as drawn here, or you can have a filled primitive as shown here. Well, we continue with the discussion of refresh rate, video basics and scan conversion. We are discussing refresh raster display systems, and we know how to draw pictures in refresh scan, but we have not moved towards demands of system memory and bandwidths and speed with respect to scan conversion. Let us take a typical example of memory usage. We will say if one uses a 512 cross 512 element raster display. What do I mean? Well, we talked of a matrix or an array of pixels. So, there are 512 rows and 512 columns, perfect square matrix, aspect ratio 1, and if we have this so many pixels on the screen, we should have also corresponding points in the frame buffer to draw a picture, and then we have, for this, if you have even talking about a single bit plane, we need 2 to the power 18 bits in the single bit plane, and that we are talking of a memory size of the frame buffer of 32 kilobytes. That is 2 to the power 18 bits or 32 kilobytes. 2 to the power 18 comes because 512 is 2 to the power 9, so 2 of them. So, we get 2 to the power 18 bits single bit plane. That means it is 0 or 1 is the value, and so we have a black and white picture on the screen. That is fine. So, for such a display system, I hope you followed the calculation that we require 32 kilobytes of memory. Well, a digital to analog converter, or the popularly what is called as a DAC, DAC or DAC, it typically means a digital to analog converter, is used to convert these bit values 0 or 1 to analog signals for refreshing the screen. The analog signals will drive the intensity of the screen. It will drive the electron beam. The strength of the electron beam in turn will dictate the intensity on the screen, and it will of course have to be refreshed. That is fine. Memory size required for an end bit plane gray level frame buffers. Okay. We talked of the previous example in this slide where capital N was equal to 1, so single bit plane, but now with this 512 cross 512 element raster display, if we keep on increasing the value of N, what is the memory required? This table shows typical examples of 3 different memory requirements for different values of N. The calculations are very simple, because when N was equal to 1, we talked about 32 kilobyte of memory. When N is equal to 3, we talked about 96 kilobyte, which is nothing but 32 multiplied by 3, and you can keep doing that. 32 multiplied by 8 when N is equal to 8 will give it 256, and for 24 you talk about 768 kilobyte or about 0.75 megabytes of memory for n equal to 24, and we are talking of this with a 512 cross 512 element raster display. If we reduce or increase the raster display size or resolution as it is talked about, the memory requirement of the frame buffer will also go up or down. Okay. Continuing, we talked about a minimum refresh rate of about 30 hertz for a random scan display system. We do not worry about that for a DVST. If you remember much earlier, I am withdrawing you back, but coming back to refresh rate for a raster display system, it is recommended to run it about 60 hertz to have no flickering, or to avoid flickering, complete flicker free display if you want. Well, you should have it more than 30 hertz scientifically, but if you have it at 60 hertz, absolutely there is no chance of any flicker which is visible to the naked eye. Okay. Coming back to memory requirements, I jump up from the resolution which we talked about in the previous slide of 512 cross 512 resolution CRT to a 1024/1024 high resolution CRT, and these are for the different values of n on the left hand side. This table shows what are the memory requirements and the display itself. Well, when capital N is equal to 1, I did say we are talking of a monochrome black and white pure display system, and we require in this case 128 kilobyte. Why? 1024 is 2 to the power 10, so we have 2 to the power 20 bits, and that gives you about 128 kilobytes of memory when capital N is equal to 1. Remember, it is very simple to calculate that, because when we had 512 cross 512, we were talking of 32 kilobytes, and that will be 4 times now. So, 32 multiplied by 4 will give you 128 kilobytes when capital N is equal to 1. Okay. Remember that previous slide, N is equal to 1, 512 cross 512 was requiring 32 kilobytes, now we require 128. When capital N becomes 8, the display, we can talk of display colors or display gray levels. We can have gray shades or colors, 256 of them instead of having just 0 or 1, and we require memory size of about 1 megabyte of about 1 megabyte, which is 8 times 128. So, that is 1 megabyte, and as we keep growing on with increasing values of N 24 and 32, we can have 16 million colors possible to display. We require about 3 to 4 megabytes of memory in the frame buffer to display a system. Now, if you look in the last 2 rows of this table, the memory requirement goes up from 3 to 4 megabytes for a 1024/1024 high resolution CRT, because the capital N has gone up from 24 to 32. I am talking about the last 2 rows. So, because of the increase in the capital N, the memory requirement is more, but we are not talking of increasing the colors. 16 million colors are the same. In fact, the extra 8 bits which are all available here are used for helping to do some other operations of hidden surface removal and shading to do with Z buffer algorithms, which we will talk about when we talk about 3D shading models later on. Okay. So, we have again at the most 16 million colors possible. Okay. Of course, if we still have, let us say at the maximum, maybe a little bit more nowadays, 32 bits per pixel possible. We talk of a very high bit frame buffer with 1280/1024 pixels rasters are available. We even talk of more than that, where one of the rows or columns can go to about 1600 pixels. Okay, that's a very large high resolution monitor, and 32 bits per pixel is typically the highest standard. Well, almost the last slide for today, before we move on to a few questionnaires, is the refresh rate of a CRT. We define this as the number of times the image is drawn on the screen per second. That is a very simple definition, but just to put it in words, we talked of a refresh rate, 60 hertz recommended, 30 hertz is the minimum. So, it is the number of times the image is drawn in the screen per second, and of course, the more the refresh rate the better, but if you reduce the refresh rate you have some advantages of reducing the frame buffer size and other advantages, but it increases flicker. The viewer may not like it if it is not flicker free. If the screen flickers, the viewer may not like your picture on the screen or your display itself, and may move over to a slightly better display with a higher refresh rate. Well, we introduce a term called horizontal scan rate. Is the number of scan lines the circuit drives a CRT display per second. Horizontal scan rate is the number of scan lines the circuit drives a CRT display per second, and we talk of this as the refresh rate multiplied by the number of scan lines. Okay, refresh rate multiplied by the number of scan lines gives the horizontal scan rate, and resolution of the screen depends on the spot size. This is very, very important. People always confuse that the resolution of the screen depends on the graphics adapter card or how much memory you have on the screen. It's nothing to do with. The display device comes, that is the monitor comes with an inbuilt resolution, and it is not dependent on the computer graphics system which you are going to use. You can connect almost any display device to almost any computer graphics system. They must handshake in the sense that the computer graphics system must know what's the resolution on the screen, whether it's too high, whether it's too low. Of course, if it is too high, some graphic system which are low end may not be able to drive the display system. That's possible, but when we're talking of resolution of the screen, it is dependent on the display system, and it is dependent basically on the spot size. What do you mean by spot size? Physically, this very small dimension of the pixel screen which grows on the screen, that spot on the screen, it is small. We are drawing points on the screen, so physically it has a finite small size, and that spot size dictates the resolution, because you cannot pack more than a certain amount of spots in a certain dimension of the physical screen. Let us see if it could be 1 feet by 1 feet, and each of them could be as small as 1/10 of an inch or something. So if you're talking about 12 inches by 12 inches, you can pack say 120 of those spots in each horizontal row or vertical column. So the spot size dictates the resolution, not the graphic system which you're using. It's very, very important. CRT resolution is not a function of the bitmap resolution. I repeat, it is similar that the spot size dictates the resolution, and the resolution is not a function of the bitmap resolution on the display device, on the graphic system, but it is basically a function of the spot size. For larger spot size, you can have it, but resolution will be very poor. You can have a very poor resolution with a larger spot size. It's better to have small spot size, but there are manufacturing limits of manufacturing technology which cannot make the spot size smaller than a particular limit. The last point in this screen and the lecture today is that the horizontal resolution of the screen spot size dictates the resolution, and the resolution again also depends on the spot size and the speed at which the beam can be switched on and off. Why this is necessary? The beam is moving from left to right at a very fast speed, and we are drawing point. To draw the point, we make the beam on at a particular pixel and then go off, on at a particular point and go off. So to keep doing this for as many pixels on the line which you need to switch it off. It could be 1, 2, or maybe a few more, maybe a few hundred points have to be turned on and off, or maybe alternate ones. Make it on, go off. Make it on, go off. That dictates. So we stop here with this lecture.